So in this question, we're asked to find an expression for voltage V, which we can see here in the diagram, in terms of current at the source, I, which is also marked in the diagram here. And we're going to be using KVL and KCL. So that's Kirchhoff's voltage law and Kirchhoff's current law. So the final answer to this question is basically an equation, which is V equals some function of I. So let's start this off by using KVL, and that's basically sum of voltages is equal to 0. So any voltage gained in our circuit has to also be cancelled out by a loss somewhere else. So looking at our circuit as a whole, we've got a voltage source. So that's going to provide voltage into the system. So I'm going to have it as a positive in my equation. Moving around, I know that I'm going to drop some voltage across the resistor. So let's give that a name. So the voltage drop across here, let's call it, say, V1. So since it's a drop, it's going to be a negative in my equation. And then we know we're going to drop some voltage across these components which are in parallel. And the voltage drop across the whole thing, let's call it V2. It should be the same across both paths. Okay, so minus V2, since again it was a drop, has to be equal to 0. So the next thing is to try and figure out how we can get I into our equation, since we want V as a function of I. And that's really going to happen by looking at Kirchhoff's current law. So let's look at the voltages that are happening around our system. So we know I is the voltage that comes out of the voltage, I is the current that comes out of the voltage source. And then because this is directly connected, I would expect that we'd have the same current running through here. Now where it gets tricky is when we get down to this point, the current is going to have to split across two different paths. So if I look at what's happening at this node, I'm going to have that I coming into the node, and then it splits off into two paths out. So you can call it whatever you want, but I might call it I1 and I2 as our two different paths. So in a moment, we're going to have to relate these I1 and I2 back to the I, which is what's coming out of our voltage source, and we're going to do that using KCL. Just before we get to that though, we can deal with this one here because that one's pretty easy. We already know the current through it in terms of I, which is what we wanted. So we're looking at resistors here, and we want to know the voltage drop across the resistor because that's what's in the equation. So I've made a little bit of a cheat table over here, which provides you with the voltage and current expressions for each of your different components, resistor, capacitor, and inductor. So we're obviously interested in resistor, and we wanted the voltage in terms of current and resistance. So we can say the voltage across our resistor is equal to the current through it times by its resistance. So let's go back and use that in our equation. So that means that we can write V1 here, it's equal to the current going through it, which is I, times by the resistance, which is RA. Alright, so that one's already done. So this one here is where it gets a bit more tricky because we know the current going through each of these resistors. Right, this one is going to be the I1, this one is going to be the I2, and we know the voltage drop across both of them. It's just that we don't really want it in terms of these I1 and I2, we want it in terms of I. So let's do a side step over here where we used Kirchhoff's current law, which is that the sum of the currents at a node has to be equal to 0. So essentially any current in has to be equal to the current that goes out. So this is our node that we're going to focus the equation on. So coming in, we have I, and then going out, we have I1 and I2. So that's why they're going to be negative, because they're going out. So let me rearrange this equation. So we're going to get, I equals I1 plus I2. And let's, at this point, substitute out I1 and I2 based on the resistances and the voltages. So if we go back to this cheat sheet thing, what we can see is that for a resistor, the current going through it can be rearranged to V on R. Alright, so let's look at I1 then. We know it's equal to V on R. So we just need to put the right notation on here. So I1, all right, the voltage drop across this resistor is equal to V2. So that's going to be the subscript. And the resistance is going to be RB. If we do the same thing now for I2, all right, the current going through here, it's going to be the voltage across it, which is V2, it's the same drop, divided by the resistance. So this time the resistance is RC. So we can substitute these two back up into I. So now we have V2 in terms of just I, which is really good because that's what we want to substitute back into this equation. So we just need to rearrange it to get V2 equals something. So we can have I equals, if I factorize out V2, it would be 1 on RB plus 1 on RC. And then V2 on its own all of that times I. All right, so let's go back and substitute these two into our equation. So that's what we get, and it's all equal to 0. So now we're pretty much at the point where we just have to rearrange this equation to get V equals something in terms of I. So I can flip these to the other side. So that would leave me with RA times I plus all of this mess, B times I. And of course, if you wanted, you could always factorize out the i's as well. But that's pretty much the final equation that we're looking for. So the only other thing I want to point out is that if you wanted to, an alternative would be to use the equivalent resistance formulas. And in fact, this would actually be an easier kind of pathway to the final answer. It's just that, yeah, I guess this is how you derive those equivalent resistance formulas. So if you have two resistors which are in parallel, in fact, the equation for the total resistance that they provide, let me pop it here. So 1 on R tot, the total resistance, is 1 on R1 plus 1 on R2. That's the equivalent resistance formula. So what you'll actually find is that we kind of prove this. All right, down here, this part here, the 1 on RB plus 1 on RC, is the same as what we've got up here in the equivalent resistance equation. So it's exactly the same thing. So that's all there is for this video, and I'll see you in another one.